In the fourth module of chapter 5, we shall learn about the fundamental theorem of a space curve. The fundamental theorem for a space curve is very important concept for the geometry of a space curve. In our earlier modules, we have seen Sennett-Freinet formulae, the intrinsic derivatives and other concepts about the space curve. Now, we are in a position to state and prove the fundamental theorem for a space curve. So, let us see the statement and the proof. So, in the fourth module of chapter 5, we shall learn about two things. The first one is the fundamental theorem for space curve, and the second one is the involutes and evolutes. Now, let us state the fundamental theorem for space curve. Let kappa s and tau s be continuous functions of a real variable s, where s is the arc length and it is considered as a parameter for the space curve, and it is defined in an interval 0 less than equal to s less than equal to a. Then there exists a space curve for which kappa is the curvature and tau is the torsion, where s is the arc length measured from some suitable base point, and such a curve is uniquely determined within a Euclidean motion. So, the two functions, two continuous functions kappa s and tau s are enabled to get a space curve whose curvature is the kappa s and torsion is tau s. So, let us see the proof of this theorem. It is a very important theorem for the geometry of space curve. Let us consider the system of differential equations of the form d alpha ds equals to kappa beta, d beta ds equals to minus kappa alpha plus tau gamma, and d gamma ds equals to minus tau beta. So, this is the system of differential equations. From existence theorem of these differential equations, we know that they admit a unique set of solutions which take a prescribed value alpha 0, beta 0, gamma 0 at s equal to 0. That means, at initial point at s equal to 0, they are taking the value alpha 0, beta 0, gamma 0. In particular, there exists a unique set alpha 1, beta 1, gamma 1, which takes values 1, 0, 0 when s equal to 0. Similarly, we can consider there exists a unique set alpha 2, beta 2, gamma 2, which takes values 0, 1, 0 and 0, 0, 1 as initial values. And also this alpha 1, beta 1, gamma 1 satisfies this relation, that dds of alpha 1 square plus beta 1 square plus gamma 1 square equals to twice alpha 1 dash. That means alpha 1 dash is the derivative of alpha 1 with respect to s. Similarly, beta 1 dash plus gamma 1 dash, and they are coming equal to 0, which implies alpha 1 square plus beta 1 square plus gamma 1 square equals to constant, and alpha 1 square plus beta 1 square plus gamma 1 square at s equal to 0 is equal to 1, because we have taken that at s equal to 0 the alpha 1, beta 1, gamma 1 is taking the values 1, 0, 0. So, alpha 1 square plus beta 1 square plus gamma 1 square at s equal to 0 is coming equal to 1. Similarly, the other two relations follows, that alpha 2 square plus beta 2 square plus gamma 2 square at s equal to 0 equals to 1, and alpha 3 square plus beta 3 square plus gamma 3 square at s equal to 0 is also equal to 1. Also, DDS of alpha 1 alpha 2 plus beta 1 beta 2 plus gamma 1 gamma 2 equals to 0. This is coming because we have taken the differential equations in this manner. So, we are putting the values of differential equations which we have taken at the first, and we are putting these values to get the expression is equal to 0. So, which implies that alpha 1 alpha 2 plus beta 1 beta 2 plus gamma 1 gamma 2 is equal to constant, and alpha 1 alpha 2 plus beta 1 beta 2 plus gamma 1 gamma 2 at s equal to 0, it is coming to equal to 0. Similarly, alpha 1 alpha 3 plus beta 1 beta 3 plus gamma 1 gamma 3 at s equal to 0 will be equal to 0, and alpha 2 alpha 3 plus beta 2 beta 3 plus gamma 2 gamma 3 at s equal to 0 equals to 0. So, by these 6 relations we get the matrix A is equal to alpha 1 beta 1 gamma 1, alpha 2 beta 2 gamma 2 and alpha 3 beta 3 gamma 3. This 3 cross 3 matrix is orthogonal because A transpose equals to identity. Now, if we consider this alpha 1 alpha 2 alpha 3 as a vector T, beta 1 beta 2 beta 3 are the components of the vector n, and gamma 1 gamma 2 gamma 3 are the components of the vector b, then we can see easily that they are mutually orthogonal unit vectors. By the above relations we are getting that these T n b are mutually orthogonal unit vectors. Now, if we consider the gamma equals to 0 to s t ds, or rather we can say this one as r also, r equals to 0 to s t ds, then r, which is a function of s, represents the curve for which T n b are tangent, principal normal and binormal respectively. Kappa is curvature, tau is torsion and S is arc length. Hence, the existence of the required curve is proved. So, by the help of that T, we can define or we can take R as 0 to S T ds, which represents the required curve. So, this proves the existence of the space curve with the given conditions. Now, to prove the uniqueness, let there are two curves C and C dash defined in terms of their respective arc lengths S, and let points with the same values of S correspond. Then, if the curvature and torsion of C have the same values as the curvature and torsion at the corresponding points of C dash, then we can claim that C and C dash will coincide. Now, how we are claiming that one? We will see in the following way. Let C dash be moved so that the 2 points on C and C dash corresponding to S equal to 0 coincide. So, at S equal to 0, C and C dash have the same point, but for others they are different. And suppose that C dash is suitably oriented so that the two triads T N B for the C curve and T dash N dash B dash for the curve C dash coincide at S equal to 0. So, at S equal to 0, we are taking the two triads also same. Then, if we calculate the derivative of T dot T dash with respect to S and applying the Sennett-Freinet formulae, we get T dot kappa n dash plus kappa n dot T dash. And for d ds of n dot n dash, we are again using the Sennett-Freinet formulae and we are getting this expression. And for also d ds of b dot b dash. Now, if we add this one, d ds of t dot t dash plus n dot n dash plus b dot b dash is coming to 0. Now, when S equal to 0, this t dot t dash plus n dot n dash plus b dot b dash equals to 3, and that means this is the sum of 3 cosines which is coming to 3, and it can happen only when each angle is 0. That means t and t dash coincide, n and n dash coincide, and b and b dash coincide at all corresponding points. Thus, d ds of r minus r dash is equal to 0, and which gives r minus r dash is a constant vector, but r minus r dash is equal to 0 when S equal to 0. That means r equal to r dash for all values of S. So, this proves the uniqueness of the space curve. That means, we are positioned to say that if kappa s and tau s are two functions, are two continuous functions of the arc length s, then we can determine a space curve R which is unique. Thus, C and C dash are identical within a Euclidean motion. Hence, the theorem is proved. So, we have proved the fundamental theorem for space curve. Let us see an example for this one. Suppose the intrinsic equations are given by this one, kappa equals to root 2a by 2a square plus b square to the power half 1 by s, and tau is b by 2a square plus b square to the power half 1 by s. That means, kappa and tau are the functions of s. Then we can easily prove that there exists a unique curve whose Cartesian equation is x equals to a e to the power u cos u, y equals to a e to the power u sin u, and z equals to b e to the power u. That means, if kappa and tau are functions of s within a interval of s, then we have a unique space curve whose equations are given by this one. Now, for that theorem, we can have a corollary that the equation tau equal to 0 characterizes the plane curve. That means, if the torsion is 0, then the curve is a plane curve. We know from Serret-Frenet formulae that del gamma I del s equals to minus tau mu y. This is the third Serret-Frenet formula. Now, if tau equals to 0, then del gamma I del s equals to 0, which implies gamma I are constant. So, binormal vector has no change along the curve. Therefore, the curve lies on a plane. Conversely, if the curve is a plane curve, then binormals are parallel, because the curve is totally lying on a plane. So, the binormals which are normal to the plane are parallel. That means, there is no change in the binormal. So, del gamma I del s equals to 0. So, again using the Serret-Frenet formula, that is the third Serret-Frenet formula, del gamma I del s equals to minus tau mu y, we have minus tau mu y equals to 0. But mu y equals to 0 is not possible, because mu y is the unit principal normal vector. So, the components of mu y are not all 0. So, obviously, tau equals to 0. So, this is the necessary and sufficient condition for a curve to be a plane curve, that tau is equal to 0, that is the torsion is equal to 0. we can get other two corollaries also in a similar manner, that a plane curve is entirely determined by the function kappa. As tau is equal to 0, so a plane curve is entirely determined by the function kappa apart from a rigid motion, and the curve may be determined by the quadratures. And the next one, there always exists a plane curve having a given continuous function kappa as a curvature. So, we can consider these two corollaries as a fundamental theorem for a plane curve. These two corollaries will give the existence and uniqueness for a plane curve. Now, we just give the concept of involutes and evolutes. Involutes of a curve are curves on the corresponding tangent surface which are orthogonal to the generating tangents. That means, the curves on the tangent surface are orthogonal to the curve, then the curve is called involute. If C is given curve and sister is its involute, then the tangents to C star must intersect the given curve C orthogonally. By the definition of involute, we are getting this, and C is known as evolute of C star. So, if C star is the involute of C, then C is called the evolute of C star. So, in the fourth module of chapter 5, we have learned a very important theorem about the space curve, which is known as the fundamental theorem for a space curve, which asserts that if kappa s and tau s are two continuous functions within a given interval, then we can uniquely determine a space curve within a rigid motion. This is a very important concept for the geometry of space curve, and which gives us the way to get a space curve when kappa s and tau s are given. We have seen an example regarding this, and we have also introduced just the concept of involutes and evolutes. With these things, we end this module of chapter 5.